Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, Chemical Bonding. Today we will begin with lecture 17 from the course, but make sure you have watched the previous ones before viewing this one. So in this lecture, the topic today is going to be the coordinate bonds and their characteristics. Well, you would say that you've already studied about this with me while we were discussing the lowest structures. But well, there is a lot more to add into this. So all those who have watched the previous lectures, please do watch it again. This is going to be very interesting. And certain important things we are going to cover, which we could not when we were discussing the lowest structures and the formal charge. All those who are watching this for the first time, please make sure you have watched the lectures on the lowest structure and formal chart before you watch this lecture. Otherwise, there would be certain things that would not be clear with you, right? So let us begin the study of coordinate bonds. So if you see this over here, we have coordinate bond, and the coordinate bond is also called as the dative bond, and there is a number 3 in front of it, which means that we have already studied about two bonds, that is the ionic bond and the covalent bond, right? So this would be the third in number that we are going to study today. All right. Now, to understand what is the coordinate bond and its difference from the ionic and covalent bond, let me give you an example. And the example is from your own classroom when there is a lunch break. The teacher is sitting in, the students are having food, and what the teacher notices is that in one corner there is one boy which he has lots of food with him. He is eating it, but he could not complete it. And now that boy is very much worried that how should I finish this food of mine, because otherwise if he doesn't finish the food, the teacher is going to scold him a lot. Okay, so what he does is he looks here and there and he finds that there is one boy who is not eating anything. So he just asks him, why are you not eating your food? He says, well, I forgot to get my lunch box. And what he does is that he says, do not worry, just have my food, I am finished, right? The boy who has got the food is happy. The boy who has given the food is happy because he wanted to finish his tiffin box, right? This is the example of our ionic bond, where there is a transfer of electron from one atom to another, and both of them are happy, one after losing and one after gaining, and there is a friendship developed between two of them. The next example is that of another pair of children. One forgot to get his vegetables and the other forgot to get his chapatis. Now both of them are unable to eat their food. So what do? They put their tiffin boxes in front of them and both of them share, one having the chapati from the other and one having the vegetable from the other, and both of them, they are able to eat the food. This would be the example of a sharing and sharing of electrons, which is going to mean a covalent bond. Now the next two students that we are going to study is going to be one boy who has food which is enough for him, right? If he does not share it with anyone, then also that food is enough for him. But he has a friend who has forgotten to get his lunch box. So now what he does is he said, do not worry, I have my tiffin with me. You just come and sit with me and have something from me. Right? This is an example of a coordinate bond. There is an atom where there is electrons which he can share with another atom, and then there is another atom which does not have the complete octet and he is sharing those electrons. So what we get over here as the definition of the coordinate bond is that this is a special type of covalent bond in which both the electrons of the shared pair are contributed by the same atom. So one atom giving all the food, right? And it is being shared by both the atoms. Fine. I hope this is understood by you people. So this is a type of covalent bond. Sharing is happening, but the electrons, they are not contributed one each by both the shared atoms forming the bond, but it is by one atom only, right? Now, what should be the condition for this? The condition should be that the donor atom of the bond, he should have a complete octet, while the acceptor atom must have some incomplete octet to form a coordinate bond, right? So we have a boy who has a tiffin box, which is sufficient for him, but there is another boy who does not have a tiffin box. His octet is not complete. So both of them, they are sharing that food and forming a bond between themselves, a good friendship. Fine. So I hope this much is clear to you people. So you can see over here, we have an atom A, and atom A's octet is complete, whereas atom B, the octet is not complete. You can see there is 6 electrons with this atom, right? So this is going to be the donor atom. This is going to be the acceptor atom. This donor atom is going to share this lone pair of electrons with atom B and form a bond which is called as coordinate bond, and we denote it by an arrow. An arrow points from the donor to the acceptor, showing that the electrons has been donated by this atom towards the atom B, right? Next, we can represent this by a covalent bond. How do we do that? Well, to replace a coordinate bond by a covalent bond, we do assign a positive charge on the donor and a negative charge to the acceptor, like this way, right? So there is a bond between them, and atom A has positive charge and atom B has negative charge. Now, how do we explain these charges on there? Well, this is the lone pair of electron, which you can say this is going to form the bond, right? Now, whenever a covalent bond is formed, atom A would give one electron, atom B would give another electron. So, from these two electrons, one of the atoms has to be supplied by A, so that it has kept in the center. And the second one, which was extra to it, we can say that it has moved from A to B. So when an electron is lost by atom A, we say that it is going to be a positive charge. And when an electron has been gained by atom B, this is we are going to call as a negative charge. So that is why we say that there is going to be a bond between them, but atom A will be having a positive charge and atom B will be having a negative charge, right? So I hope this is clear to you people how a coordinate bond is formed when there is going to be a covalent bond between the two atoms, but the shared pair of electrons contributed by one atom only. So during dative bond formation, the shape and the hybridization of the acceptor molecule changes, but in case of the donor molecule, only the shape is going to change. This is something that you will be able to understand when we have discussed the theory, that is the valence bond theory, where we will be discussing much more about the shape and hybridization of the molecules. But still, you can just keep this in mind that you have to remember this thing as well. Okay. All donors, they act as Lewis bases, and acceptors, they act as Lewis acids. Well, till now, that is in class 10th, what you have learned about acids and bases is that acid is one thing that is going to release H ions, and base is one that is going to release OH ions. But there are certain more definitions about acids and bases which you will be learning in the course on chemical equilibrium. Okay, so this is also in 11th only, where you will learn that what are Lewis acids and what are Lewis bases. Lewis acids will be the molecules or the ions or the atoms where they can accept an electron pair, whereas Lewis bases will be the one which can donate an electron pair. Okay, so here we have a Lewis base because this donor atom A, it can donate its electrons to atom B, and atom B, this is accepting that lone pair of electrons, so therefore it is called as a Lewis acid. Fine. More about it you will be discussing in the course on chemical equilibrium. Now the compounds which contain the unshared pair of electrons or the lone pair of electrons, they are the ones which readily form the dative covalent bonds or the coordinate bonds. For example, when ammonia is mixed with gaseous hydrogen chloride, white clouds of ammonium chloride are formed. And the formation of this ammonium chloride involves the formation of a dative bond between nitrogen atom in ammonia, which consists of the lone pair, and H positive ion from HCl. Let us understand this with this figure over here. We have ammonia. If you draw the Lewis structure for it, nitrogen is going to be the central atom, hydrogen being the corner atoms. There will be formation of single bonds first of all, and then you will see that the duplet of hydrogen is complete, and nitrogen, after forming these 3 bonds, it will have 6 electrons plus these 2 electrons as the lone pair of electrons. So the octet of nitrogen is complete. So the first necessary condition for the formation of the coordinate bond is that this molecule, the atom is there which has a lone pair of electrons plus the octet of this atom is complete, right? Now it is in a position to donate electrons. And whom is it donating electrons? It is donating it to a H positive ion, which does not consist of a single electron, right? So H positive is formed by the loss of the electron which hydrogen atom had. So now when this nitrogen puts this lone pair of electrons in the center, there is going to be the formation of a coordinate bond between this nitrogen and hydrogen, and what we get is a ammonium ion over here. So the positive charge which was on nitrogen, when you will calculate the formal charges, that will come on the nitrogen atom, but we say that it will be always on the complete ion itself, right? So this is what we have as the ammonium ion, and this is the example of a coordinate bond being formed between the two, and the reaction giving us the formation of ammonium chloride, NH4 positive and Cl negative. Similar reaction occurs and hydronium ion is formed when HCl this dissolves in water. So let us understand that also. When there is HCl plus water, the HCl is going to ionize to form H plus ions and Cl negative ions, right? So this H positive is going to react with water molecules to form the hydronium ion. So we see in the water molecule, after forming 2 bonds with hydrogen, oxygen has 2 lone pair of electrons, and this is 1 lone pair of electrons. It is going to share with this H positive ion to form a coordinate bond between oxygen and hydrogen, and hence we will be getting the hydronium ion. Okay, fine. I hope this is clear to you people. So now let us see some more examples from the coordinate bond. The first one is the ammonium ion, which we have already done. Here what you can see is now that nitrogen has 4 bonds which it has formed, and the angle between all these bonds, this will be 109.5 degrees, right? The next example is of an ozone molecule. So the ozone molecule, the Lewis structure also we have done earlier, and what we have seen over there was that there was a central atom, and here we have an oxygen where there is going to be a double bond, right? So oxygen double bond forms a oxygen molecule, and this is one molecule which has an independent existence because octet of both these molecules would have been complete after that. 8 for this and 8 for this, right? If you just not consider this circle over here, this would be 8 electrons for this oxygen and 8 electrons for this oxygen. But yet this oxygen, because it has 2 lone pair of electrons, it can donate these electrons to another oxygen atom and form a coordinate bond over here with this oxygen. So this oxygen had 6 electrons, this had 8 electrons, and it has donated these 2 electrons, or not donated, actually sharing the 2 electrons with this oxygen atom, and now the octet for all of them, this is complete. And what we have over here is a ozone molecule with the coordinate bond between these 2 oxygens and a double bond between these 2 oxygens, right? So this is how we are going to represent the molecule. double bond between these two and a coordinate bond between these two, right? So next we have the carbon monoxide molecule, and we see that there is a coordinate bond formed between this oxygen and carbon, right? And the electrons, they are being donated by this oxygen atom. Now you can even understand this again, although we have discussed the Lewis structure for this before also, that there are going to be two electrons and two these four electrons as far as the oxygen's lone pair of electrons is concerned, and two would be this double bond had this coordinate bond not been there, right? So octet of oxygen would have been complete, but for carbon what you would have seen is that there would be two electrons plus four electrons of these double bond, that means six electrons, the octet not complete. So oxygen, this is extending it two electrons for sharing with carbon so that the octet of carbon also completes, and hence we have a coordinate bond formed between the carbon and oxygen atom, and CC as a carbon oxygen triple bond. Next we have nitrogen trihydride boron trifluoride. What is going to be this? Well, this is NH3BF3, and let us see how a coordinate bond is formed between these two. Well, you now know the structure of ammonia, that there is a electron pair on nitrogen, and BF3 molecule, if you remember while we were discussing earlier also, that boron atom, this consists of 6 electrons. The octet of boron is not complete, and this is one of the limitations also as far as the Lewis octet rule is concerned, that this molecule does exist although the octet of boron is not complete. Now, if the octet of boron is not complete and nitrogen has an extra electrons which it can share with this boron, so there is going to be the formation of a coordinate bond between nitrogen and boron. Nitrogen keeping its lone pair of electrons in the center and sharing it with the boron atom, right? And this is how we see the formation of this nitrogen trihydride boron trifluoride. Okay, next we have is the sulfur dioxide molecule. In this, what you are seeing over here is that there is a double bond between sulfur and oxygen, and the lone pair of electrons on sulfur, it has formed a coordinate bond with oxygen, just similar to what we have done for the ozone molecule. Next, we have the sulfur trioxide molecule. So here what you are seeing is that although this lone pair of electrons, it was still available to this sulfur dioxide molecule. So the sulfur dioxide molecule's lone pair of electron, it can form another coordinate bond with another oxygen atom, and we see the formation of sulfur trioxide by the formation of two coordinate bonds for the two lone pair of electrons on sulfur. Right? So this is how the sulfur trioxide molecule is formed. So next we have is the HNO3 molecule, that is the nitric acid, which you can easily understand that formation of two bonds here and third bond here. Nitrogen has two electrons which are the lone pair of electrons, which is going to be extended to the oxygen atom to form a coordinate bond, right? And hence this is how we are going to get the structure for the HNO3 molecule. Now coming up to the triiodine ion, this is an interesting one. This is I3 negative. Now an example where this I3 negative is being formed is when the iodine is being dissolved in aqueous potassium iodide solution. So this is I2 plus I negative forming I3 negative, that we see the formation. Okay, so what is going to be the structure for this ion? We have one iodine atom, 7 valence electrons, another iodine atom, 7 valence electrons, both of them keeping one in the center forming a bond. We get the formation of a I2 molecule. Now this is an I2 molecule with 8 electrons in this and 8 electrons for this, so the octet is complete. This is an iodide ion. In case of an iodide ion, there is a gain of 1 electron to the iodine atom to form the iodide ion. Hence this ion also has a complete octet. Now what happens in the formation of the I3 negative is that it is this iodide ion which is going to extend one lone pair of electrons to this iodine atom to form a coordinate bond. Okay, so the central atom will now have 10 electrons. right? It will be 10 electrons, out of which 4 will be the bonded pair of electrons and 6 will be the lone pair of electrons. Okay, the shape of this molecule, this is a linear molecule. How we come to know about the shape, or how we come to know that the coordinate bond has been formed? By the extension of the lone pair of electrons from this iodine to this iodine atom, is something that you will come to know when we study the VSEPR theory. Okay, so till then you just remember that it is this iodine atom which has extended its lone pair of electrons to form a coordinate bond with this iodine atom of the iodine molecule. Okay, next we have is the aluminium chloride crystals, that is AlCl3. Now what we see in AlCl3 is again that the aluminium atom is going to have an incomplete octet in the formation of aluminium chloride. There are going to be 6 electrons for this aluminium. That means this is also going to be an electron deficient molecule. Now this electron deficient molecule tries to complete its octet by combining with another aluminium chloride molecule. So what we have as a result is the formation of Al2Cl6. How is it that so? This chlorine atom of the second aluminium chloride molecule is extending its lone pair of electrons to form a coordinate bond with the aluminium atom of the first molecule, and the chlorine of the first molecule, the lone pair is being extended to the aluminium of the second. Right, so one coordinate bond here, one coordinate bond here. What we are getting is a crystal formed in case of aluminium chloride. The solid state aluminium chloride, therefore this is ionic. It forms the ionic coordinate lattice, but it has significant covalent characteristics. Okay, so what we are seeing is this crystal lattice type of a thing which is being formed in the case of aluminium chloride. The next example where we can see a coordinate bond is in case of a hydrated cation. Hydrated cation means a cation which is associated with water molecules. So the bond between the water molecule and the cation in this case would be a coordinate bond, and every water molecule is attached making one dative bond. For example, we have AlH2O6 water. This means that we have an aluminium ion, aluminium 3 positive, which is associated to 6 water molecules by 6 coordinate bonds. Next we have is BeH2O4 2 positive. Again the cation is Be plus 2, and this is formed an association with 4 water molecules. This is going to be the hydrated beryllium ion, and here there are going to be 4 dative bonds between beryllium ion and water. Now, the next example of a dative bond is the bond between the ligand and the metal atom in case of complex coordinate compounds. Well, this is something that you will be studying more in class 12. But just to give you an example, here you can see in this square bracket, what you have over here is copper NH3,4 sulfate. Okay, so this portion of the compound, here you have a metal and this is going to be the ligand, and there are going to be coordinate bonds between this metal and ligand. Okay, details you will be understanding more in class 12. You can see just simply that there are going to be 4 coordinate bonds between copper and ammonia. Next example, similarly, you can see over here in this bracket again is going to be a nickel and 6 water molecules. So there are going to be 6 dative bond between nickel and water in this coordinate compound. The properties of the coordinate compounds, let us understand them also. They are going to be intermediate between the properties of the ionic and the covalent compounds. So the coordinate compounds, they can exist as gases, liquids, as well as solids under ordinary conditions. The melting and the boiling points are somewhat in between those of the covalent and ionic. They will be more than the covalent and less than the ionic substances. They are less soluble in polar solvents like water, but readily soluble in non-polar solvents like benzene and carbon tetrachloride. They are just as stable as the covalent compounds. Like covalent compounds, the coordinate compounds, they are poor conductors of electricity and they undergo molecular reactions. And finally, the dative bond is a strong bond and this has a directional nature. So now coming up to the last but not the least important slide of this lecture. This is an edge section for you wherein we put certain things which are going to be really beneficial for you in the competitive exams, and this will help you excel over other students. First important thing that you remember over here is that once a dative bond is formed, it is indistinguishable from a covalent bond. You cannot make out the difference between the two. The only difference between the two is the mode of formation. Once formed, they are just the same, and therefore the covalency of an atom is going to be the sum total of the covalent bonds as well as the dative bonds. For example, if we consider the nitrate ion, so NO3 negative, the covalency of nitrogen in this case would be 4 when you draw the lowest structure. Okay, now one more thing that I can give you as a tip over here, when you are given a question where you have to find out which of the molecules or the ions they have a coordinate bond, what you can do over there is just check the covalency of the central atom. When you check the covalency of the central atom, for example, in case of nitrogen, the covalency is coming as 4. What is the ground state general covalency seen for nitrogen? Well, that is 3. Okay, just like in the case of ammonia. So here it is showing a higher covalency, and in the structure you will see that the octet of nitrogen is complete. Octet is complete, it is showing a higher covalency, there is a formation of a coordinate bond. Similarly, in case of sulfur, that you will see over here is we have a sulfate ion. So general covalency, the ground state covalency for sulfur should have been 2, equal to the 2 unpaired valence electrons in the configuration of sulfur, but it is showing a covalency of 6. So this means over here that there is a possibility of a coordinate bond being formed in the case of the sulfate ion. Okay, just check the covalency and whether the octet of this atom is complete. If the octet is complete and the covalency is higher than the ground state covalency, there is going to be the formation of a coordinate bond. Next, you can see in the case of oxygen, in case of H3O positive as well, the covalency of oxygen general is going to be 2. Here it is showing 3 and it is forming a coordinate bond. The octet of oxygen again in this case would be complete. All complex compounds except the metal carbonyls, like the ammonium salts, the alkali metal isonides, etc., they consist of ionic, covalent and dative bonds, all the three. So generally this type of question also comes in the examination where you have to tell which of the following compounds consist of all the three type of bonds. Another example, the hydrated complexes, like you have just now seen, the copper sulfate pentahydrate, copper sulfate 5H2O, magnesium sulfate heptahydrate, magnesium sulfate 7H2O. This consists of ionic bond, covalent bond, hydrogen bond as well as dative bond. So all four of them, they are present over here, right? So these are certain things that will really help you excel in your examinations. So that would be all for this lecture, and from the next lecture onwards we are going to start with the next theories that we have to study. The first of all which we'll be discussing would be the Sedgwick-Powell theory. So see you again for the next lecture. If you have not subscribed to the channel, please do that, and also do click on the bell icon so that you get a notification as and when we put up the new lecture for you. Also please, before leaving, if you've liked the lecture, do click on the like link. That really motivates us further. Thank you and have a nice day. God bless you.